Hello everybody and welcome to Deep Learning with Pytorch Lesson 5. Today we are going to be doing some more stuff with tensors. We're going to be finishing up chapter 3. Let me find my code real quick. Okay, here it is. So there is one thing that I forgot to do for the last lesson, which was dealing a lot with data types. So let's say we have points here. Let's say we have points 64 equals torch rand 5 type equals torch double. So this makes double. This makes float 64 tensor of 5 different points. So if we look at that, that's what it looks like there. Just 5 float 64 values, randomly generated. So let's say we make points underscore short, and the point is we could make it just like this, just say d type equals torch dot double, or we could convert it points underscore 64.2, and now we've converted that to short, which was integer 16-bit integer. So if we want to look at that, it's just going to be zeros. And as I said before, we can multiply these two tensors, end up being a float 64. So I guess depending on which once you multiply, it'll go to a data type of one of those two data types. Let's say, what if we didn't do short? What if we did float? Then we shouldn't get zeros, right? Yeah, so we don't get zeros. So this is a float 32. This is a float 64. It ends up being a float 64. What if we made this a float, and we made this a long integer? Which one would it be then? It doesn't tell us. Let's see. It ends up being a float 32. Okay. So I guess it automatically goes to float, and then after that it just goes to whatever the longest bit length is. So that's just a quick point. The main point of this is to show you the ability to convert tensors of different data types to tensors of another data type. So now let's start on the next lesson here. And we're basically going to be showing how the computer looks at these tensors, okay? So what if we have a transpose? And that's how you do the transpose, by the way. You actually need to do this too. You need to specify the matrix that we are transposing and the axis which we want to transpose to. And now we have A, and we also have A underscore T, which is the transpose of that matrix. Real quickly, I'll go through this. This is an important page in the book. These are all the different operations we can perform on a tensor. So we have creation ops, functions that construct a tensor, like ones from NumPy, or zeros, or just writing the whole tensor in value. We have indexing, slicing, joining, and manipulating ops, functions that change the shape, stride, or content of a tensor, like transpose, which is what we just did. We have math ops, functions that add, or I guess they're all listed here, right? Pointwise ops, stuff that does a function to each element. Reduction ops, functions computing aggregate values by iterating through tensors like mean, standard deviation, norm. Comparison ops, we take the equal or the max, or is it less than that type of operations. Spectral ops, functions for transforming in and operating in the frequency domain shift, like these two commands here. Other operations, special functions operating on vectors like cross or matrices like trace, which just takes the diagonal. Blas and Lepac operations, functions following the basic linear algebra subprograms, specification for scalar, vector, vector, matrix, vector, and matrix, matrix operation. We can also do random sampling, serialization, and parallelism as well to matrices and tensors. So this is all the stuff that we can do to tensors. So if you understand most of these, then you are on the right track. Now let's look at how a computer looks at this process that we just did, right? We have a we had all ones, 3 by 2 ones matrix. And basically how the computer stores it is just in one row. So that's how the computer's looking at it. And it will basically, it changes the stride based on what the tensor is. So the A and the A sub t, if we go back to that, it's stored in the same place, just the stride is different. And we're going to see the stride. We're going to get some good examples of that. So if you don't know what I'm saying, don't worry. We're about to do that right now. Let's get a little more familiar with the transpose here. Let's say torch.rand. Let's do three values by 2. Row length 3 columns, or 3 columns, 2 rows. And now let's take the transpose of that. And this is just another way to do transpose. Here I specified A here. In this case, I'm just saying A dot transpose. So it's just another way to do it. And we can say 0.1. And then we got that. Let's see, what's the shape of these? Okay, so we got one that's 3 by 2 and one that's 2 by 3, because that's what the transpose does. What if we switch this? 1, 0. We'll get the same thing, because we have that number of, if you flip it on this axis or that axis, it's the same thing. Like even if we said print A and print A underscore T, we will get the, see, there's always easy ways to make mistakes there. That has to be a lowercase p. The same thing for 0.4994. If we switch the axes, it's just going to be the same thing. Where this would get confusing is when we have, it's not a 3 by 2 anymore, it's a 3 by 3, or you're taking the transpose of a 3-dimensional tensor. It gets confusing quite quickly in those cases, but not impossible. So let's look at that same matrix that we have here and get some physical examples of how the computer is storing this, and we can do that in the code actually. So right here, points 1 let's say 4, 1. And so where did I mess up here? So we need this. Now we have a points 1 tensor. And we're going to keep using this, so be ready to copy and paste it a lot. So that's what it looks like. But how does it look like in storage? So we just say dot storage, and that's what it looks like. It is just a one-dimensional vector. The computer is always storing these as, you could think of it as a one-dimensional vector. It's just a straight line of numbers. All right, let's say points storage equals points. So now we're creating a new tensor from the old tensor. Okay, so we're off to a tough start here. Points is not defined. We're dealing with points 1 here. Okay. So this is called points 1. So we got to put a 1 in right here, and then now we'll have a matrix, a tensor. I keep mixing those up because it's 2 dimensions, so it is a matrix, but everything in Pytorch is a tensor. Everything is stored as a tensor. So let's say we want to look at points underscore storage 2. Okay, so that's a 5. And that's because it goes 0, 1, 2. So it's not too complicated. If we go for the second one here, 0, 1, 2, we'll get the 5. If we go for the first one, we should get the 1. If we go for the 0th one, we get the 4. So we're just indexing. We've done that before. All right, now let's define points. And I'll just copy and paste this here. So we're going to make another matrix just called points. And what if we say points underscore storage equals, so we're doing the same thing, points dot storage. And so I have 2 matrices. I'm defining this one here, 4, 1, 5, 3, 2, 1. And now I've made another one just out of the storage. What if I manipulate the storage matrix? So I'll say points storage, and this will kind of send everything home. We'll have a better understanding of what's going on now. So also, I should make point zeros in here too. If you don't write point 0, let's look at what that does real quick. So let's say we have this one, and then I say points dot dtype. It's a float 32. Now what if I got rid of all of these zeros? What type of data is it going to be? An int 64. So that's why you see them in the book and add these decimal places here to make the data be stored as a float. Without the decimal points, it'll just be stored as an integer. But let's go back to this example here. So we just said points storage. We're saying that this 4 here, we want to change that to a 2. Okay. So we do that. That's fine. Now let's look at our points matrix. It changed the 4 to a 2. So even though we manipulated the storage matrix, the computer is looking at the same matrix. It's looking at the same data, just calling it in a different way. So if we do any manipulation of the storage matrix, it has an effect on the original matrix as well. So it's important to know when if you want to do this, do you want to copy the matrix and make a copy of it and manipulate that so you have 2 different matrices, or do you just want to manipulate that one matrix? When you're writing code, you have to think about these things. So let's do a 3x2 again, and let's look at another command real quick. a dot 0. This is a pretty simple command. We're just going to zero out the matrix. So, this didn't work because of a simple command error. You don't just write 0, you have to write an underscore right here. And now it worked. So this was 1s in this line, and now it is 0s. So simple stuff. Let's go to slide 2 real quick. So this is the important lesson to gather from all of this. And that's called the stride. And we're going to do some coding examples of the stride in a minute. Let me see what this is. Okay, we'll look at that in a second. So we have this stride here where this is our matrix, this 517, 733, 428, and it's stored in the computer like this as a one-dimensional vector. The way the computer organizes this into a tensor is by something called the stride. So it says every 3 values you start the next row, and then you go 3 more values and you start the next row. So 5 to 1, start another row, start another row. So when you define a tensor, it's just saying here's the data, and then it looks at what your stride is, and that's that. It will manipulate the data according to that. So and +1 would be the next column. So every 3 is the next row, and every 1 is the next column. So it goes 1, 1, 5, 7, 4, 5, 7, 4. So that stride is just what the computer uses to define the dimensions of your tensor. Row length, column length, all of that. So let's make that tensor. Let's make that exact same tensor that we just saw in that figure. Same values and everything. Close that off. Some mistake here. It's right here. If you see the red, that means that it's not closing anything off. So I forgot one here. And now we have that. Let's do second points equals points 1. Okay. Second so we're saying second points is this. What is second points? So we have a tensor. We defined it. It's just like what we saw in the example there. Second points equals points 1. So we are indexing again, but what are we grabbing with that? Let's look. You can always just check if you're not sure. 1, 3, and 2. We're grabbing the second row of the matrix. Second points storage offset. It is offset by 3. So I believe that means that there's 3 values there. Like if I were to quickly take these out, I'll put them back in a second. Let's see what the offset is then. 2. Okay? Very clear there. So let's put those back in. So let's finally look at the stride, because that's the main point to take home from here, and we can just look at it. Points.stride is 2.1. So it's 2.1 because I didn't update this code. Once I run this, it should be 3, 1. 3, 1. If I had 4 values, 4 values, 4 values, it would be 4, 1. So however I define this, it defines the stride as well. But it's just storing these in a one-dimensional vector. So let's keep going here. Second points equals points 1. So we already did that. Let's look at the size of second points. You have to add that to get the size. Okay. 3. If we said point size, it's going to be a 3 by 3. But second point size is just 3 because it's just simply a one-dimensional vector of length 3. And what would the stride be? Let's look at that. It's 1 because it's a one-dimensional vector, so there really is no stride there. All right, so let's grab this. Let's grab this matrix again, put it in here, and continue moving. Let's reiterate a point that we've already made, which is that what if we say second points 0? So second points is this row. The 0th value on that row is 1. What if we set that equal to 10? All right, now what if we look at second points? It is 10. But what if we look at points? It is also 10. So when we made this new tensor, points 1, it's just looking at at this tensor in a way. So manipulating this one has a direct effect on the original. Okay, we didn't make a copy of it. It's the same data. The computer is looking at the same line of data in the same stride, and so if you manipulate 1 and it's looking at that at this line of code and you change this 1 to a 10, all the tensors that are calling this line are going to see that 10 right there in that value, unless you make a duplicate or a clone or a copy of the matrix. If you're just doing it that way that we just did in our code, it will not make a new one, so it's just looking at the old one. All right, so let's keep going here. So say we don't want that. We're like, hey, that's not what we're after. We don't want it to be changing the original. We want a new matrix just of that row. So it's in this step here that we need to change it. We say clone. And now we have 2 separate matrices. And if we look at second points, we did update to a 10. If we look at points, we still have the original. So the computer wrote another storage one-dimensional vector, this here. So there's a copy of it. There's a physical copy of it. And if you're looking at this and you want to know what that 6 is, I'm really not sure. I guess it's just maybe from a different previous matrix or something. But maybe to iterate that point is that they're all strung together there. I'm not sure why that 6 is there, but it's just important to understand the concept that this is how we're storing matrices in the version of stride. Okay. So let's take this old points one here and look at points again. All right, so this was the the 3 by 2. And let's take the transpose of it. So how do we take the transpose of it? I think we did it up here, right? You'd say the matrix dot transpose. Okay, we can do that. Points underscore t equals points dot transpose. Okay, so now we have two. We have points. Now, say we want to check, is this looking at the same data? If we manipulate the transpose, do we manipulate the original tensor? There's one way to check that. So we say id points dot storage equals id. Is it looking at the same storage vector? True. It is. Okay? The storage vector is the same for both of these matrices. All right. What is the stride of these two? This one is 2, 1, and as you can imagine, the transpose should be different. It should be maybe 1, 2. 1, 2. So we're just changing the stride. The numbers are the same. The stride is what changes. That gives us different views of our matrix. Okay, sum t equals torch dot ones 3, 4, 5. Let's take the transpose of sum t. Transpose of t equals sum t and let me look at my code real quick to make sure this is correct. Yeah, it is. Okay. So when we take the transpose here, we can say 0, 2. Because we're taking the transpose of a 3-dimensional tensor, so it's a little different. And it's always going to be a little confusing when you're doing that, because it's based on which axis you define there. Okay, so our shape is 3, 4, 5. What is the transpose shape, though? That's going to be more interesting. 5, 4, 3. So it flipped these two. And you can kind of just play with it to figure out exactly what it's doing. 4, 3, 5. Flip those two. If we don't do anything, it won't do anything. Put a 2 here. 5, 4, 3. So that made the 5 go there and the 3 go there. So the 2 did the same thing. Yeah. I don't think we could put a 3 in there. Yeah, we cannot. So it takes a little more thought when you're doing the transposes here. Some t dot stride. What's the stride of the matrix? Okay. 20, 5, and 1. So that's interesting, right? It's literally saying every 20 values, that's when you'll drop in this dimensional category. Every 5 is when you drop from that dimension. And so on. So the stride gets a little more confusing in 3 dimensions. But that's how it works. It's 5 here. I guess you'd have to look at length, width, and height to get a good visualization of it, because you need 3 dimensions. And once it goes don't spend too much time with it, because once it goes to 4 dimensions, you're not going to be able to visualize it. You're just going to have to do it mathematically and make sure it lines up correctly. So now let's talk about contiguous. Is this contiguous? What does contiguous mean? Well, a tensor whose values are laid out in the storage starting from the rightmost dimension onward, that is, moving along rows for a 2D tensor, is defined as contiguous. Contiguous tensors are convenient because we can visit them efficiently without jumping around in storage. Improving data locality improves performance because of the way memory access works on modern CPUs. The advantage, of course, depends on the way algorithms visit. So, one easy way to understand if it's contiguous or not is it will not be contiguous if you have taken the transpose of that matrix. So if we say this one is not going to be contiguous. Okay? Not contiguous, because it is the transpose of that. Any matrix we write out will be contiguous, and once we take the transpose of it, it will no longer be contiguous. And there are other situations too that might end up in a matrix not being contiguous, or a storage tensor not being contiguous. All right, so I'm going to copy and paste some code in here and just go through it real quick. It's just to reiterate some of these points. So here we have a tensor. A range just takes it from that range of 1 to 13. Boom. So it just goes to 12 there. And what if we want it to change the way this is? Okay. So we have x, same line of code here. Same line there. Let's view it. X.view in a different manner and look at y. Okay, so now y is, we just changed the stride of it. 4 rows, 3 columns. And if we reiterate this point again, x 0, so we've defined x, then we defined y, then we're changing a value in x, and it will change a value in y because y was defined via x. So it changed that first number 1 to 100. And we're printing y, so it did it in both x and y because it's looking at the same locality to grab that storage set of numbers. Now let's look at this one. Okay, so now we're defining x, defining y. We're changing a value on y. So if we print y here, here's y printed before. Now we've changed a value on y. And I just wanted to show that this is -1, 1. The last row, the last column, we changed that value. We print x, and it has changed on the original matrix, as well as the matrix defined on that follow-up matrix. All right, so let's do this. So however we define the view is how the matrix will be stored. So this one is a 6 by 2. We could have done, in your math needs to line up correctly, right? You can't say 1 by 2. That won't work. It has to be 6 by 2. We could do 3 by 4. We could do 4 by 3. And we could do 2 by 6 if we really wanted to. You could even do 1 by 12, but it'll already be a 1 by 12. So, I mean, I guess you could say 12 by 1. Yeah, you could do it that way. But let's go back to the original, which was 6, 2. Okay. What's the stride of this? The view is that. Is the stride the same as the view? No, it's not. It's 2 and 1. So every 2, we drop to a new row. Every 1, we go to a new column. So to reiterate that point, is X contiguous here? Yes, it will be. We never did the transpose, so if we're not doing the transpose, the matrix is still going to be contiguous. Let's get back to the main course of the lesson here. Points underscore t. So now we've taken the transpose again. Let's look at that. We've already done this, so it's not too complicated. How about this? Storage is the same. If I do points t storage or point storage, same thing. And we look at stride. The stride will be different. So we have been speaking about contiguous, right? Points underscore t is contiguous. This command will just basically tell you if it's contiguous or not. And by the way, this is a Boolean value. It's a true or false value. That's the form of data that it is. Points t is not contiguous, right? Because it is the transpose of a matrix. What if we want that to be contiguous? Because the main thing with contiguous data is that it's easier to access, so it will improve the efficiency of our code. So we want to take the transpose, but we want to still have a contiguous form of data. Okay. Oh, I skipped a line. Very simple to do this. Now it is contiguous, so let's copy and paste that in here. Is this matrix contiguous? Yes, we made it contiguous. It basically made a copy of the original storage here, and if we make a change to points t contiguous, it will not affect the original matrix here, which was points. So let's do that real quick. Just to here's points. Here's points t contiguous. Let's say we want 0, 0 to be a 6. So now we've changed that value to a 6, right? But did that change the original one? No, because we made a copy. I mean, in order for that data structure to be contiguous, you need to make a copy of it. So we're no longer referring back to the grandfather matrix. What's the stride of this one? 3 by 1. Okay, that makes sense. So there's the thing right here, right? Points t contiguous stride is 3 by 1. So every 3 it drops to a new row. Every 1 it goes to a new column. This one says every 1 it's the same matrix structure. Every 2 it goes to a new every 2 goes to a new column, and every 1 it drops to a new row. So it's just written backwards. I mean, it's not stored correctly. So that's the main point of contiguous. I think the values need to be going in a descending order. So this one's just stored in a more efficient manner. And if we look at this storage, it'll be the same thing. We did change the 6, so same thing there. So that's one way to improve our efficiency. There are other ways to improve our efficiency as well. One of them is, where are we operating? All these operations take place on our computer. There are 2 locations where these calculations can be performed. There are 2 locations where these tensors can be stored. We define where those are stored. And just for your information, those 2 locations are the GPU and the CPU. And the big thing with machine learning, artificial intelligence, probably the reason why it has seen so much development over recent years, is because of the development. Of course, CPUs have gotten better, but GPUs have gotten way better. So we are able to perform these calculations very quickly. It's the same thing with Bitcoin mining, right? The processing power of GPUs is just so fast, and we can parallelization. We can exploit parallelization to perform these calculations in parallel in the GPU, and that's basically what gives us these faster computational speeds. So this device is CUDA. CUDA is a parallel computing platform and application programming interface model created by NVIDIA. NVIDIA is a graphics card company, so it's no wonder they developed that. And so when we write this tensor, we are saying, hey, make sure you store it on the graphics card. That's all we're saying here. Another way to do that is we can, if the matrix has already been defined, we can say, take that and put it on the GPU. So now it's taken this matrix, which may have originally not been on the GPU. It already was, but if it wasn't, we could have said, hey, take that tensor, put it on the GPU, please, and it will do that. Now, what's another way we can do that? It's the same thing here, but what we're able to specify is the location on your GPU. That's what this is specifying here. Now, most of you, if you're doing this on your PC, you're only going to be able to write 0 unless you have 2 graphics cards in there for some reason, which would be pretty cool, but most of us don't. If I write a 1 in here, I just get an error because it says, hey, you don't quit trying to flex. You only got one graphics card. Get out of here with that. So that's that. Now let's look at some new stuff here. So points was a matrix written up here somewhere. I don't remember where. Here it is. We wrote it several times, but it was written here. I did not define where this matrix was. I didn't write device CUDA. It's just written on the GPU. So this calculation is performed on the CPU. And it's not a big deal. It's just a fast multiplication. The CPU can handle that. When we get into the depths of machine learning, we're going to be doing maybe millions of calculations. So if you do it on the CPU, you're not going to be going very efficiently. Let's just put it that way. So what if we want to do a calculation on the GPU? this calculation will be performed on the GPU because we are taking the matrix points and saying, hey, put that on the GPU and multiply it by 2. So once that is on the GPU, all the calculations will be performed on the GPU. So that is why that calculation will be performed on the GPU. And any arithmetic will suffice. Like this will also be performed on the GPU. It's an addition. That's performed on the GPU. Points underscore CPU. Say we want to send it back to the CPU. That's another thing we might want to do for some reason. Just simple enough. CPU. Now that storage tensor is back on the CPU, we can pull it up. There it is on the CPU. So just to finish up this point here with a few other examples of how to transfer data from GPU to CPU. This is another way. We say points dot CUDA, that's going to send it to the GPU. Another way to reiterate the location here, right? I can't write a 1 in there. I only have one graphics card, but if you had more than one, you could do that. And say we want to send it to the CPU. You would just say points underscore GPU dot CPU. And that sends it back to the CPU. So that's the end of that one. We'll finish up in just a little bit. We're almost done here, and then we will have a good background in tensors, and we'll be ready to move forward into the more fun deep learning applications. So let's import NumPy as NP. NumPy is kind of like the OG of Python. All your math calculations used to always be done on NumPy. The reason we have Pytorch and TensorFlow is because it's just a more efficient way. You don't want to do all these calculations with just NumPy. So let's write but we still might use NumPy in certain instances. You don't want to just forget about it and not know how to do anything. So let's do a points torch.ones 3x4. Let's do a point. Say we want to send that back to NumPy. So you can't just start doing NumPy applications to this torch tensor. You have to send it back to NumPy in order to do that. So not too complicated. And now it will be in the form of an array in NumPy. D-type float 32. There's a lot of similarities between operating on tensors and matrices in Torch versus NumPy. A lot of the calculations are the same. It's not too complicated. Everything you can do, you can just pretty much Google really quick if you run into trouble and figure it out. Getting comfortable in one will allow you to get comfortable in the other one as well. So this is an example of a line of code here. Points torch from NumPy. So now we are sending it back to Pytorch. This is a Pytorch data structure. This is a NumPy data structure. Not too complicated. I'll finish up just 3 more lines of code here, it looks like. Torch.save. Say we're running this long code and we want to save some of the data halfway through, and we don't want that data to be affected by anything. We can do that. There are many ways to do this, but here's one way. Find your file name. And paste it in there with these apostrophes or whatever they're called. I don't know. In between those two. you put your file name. How do you get your file name? Hopefully most of you know this, but you could just go to wherever your file is and hit right click, copy address. Let me go ahead and run that line of code. And when you paste that in, you put the 2 apostrophes there, and all the backslashes need to be changed to forward slashes. I messed something up. Oh, there it is. Okay. Then add a backslash at the end. And what do you want to save it as? You could save it as points .t. It's saved in the form of a .t file. Okay? So when we saved this one, it went to that folder. It went to this specific folder. And we can see it right here. There it is. So now we have a record of that. And say we want to load that. Very simple. Torch.load. And then insert your file in this format. So when you copy and paste it, you need to change all the slashes again. Okay. And that's that. I hope everything was pretty clear. This is the way a computer stores these tensors. It's only changing the stride. Transposing changes the stride to a 1/3. Because it's a 1/3, now it is no longer a contiguous tensor. And writing something here will affect the original. So it's just a quick lesson on data storage and how the computer is storing this data which we are playing with. Okay, thank you very much, and I'll see you in lesson 4. And in lesson 4, we're going to be going over some more exciting stuff, real-world data representation using tensors. Okay, thank you.